What if a pair of bent crystals could unlock secrets that change our understanding of the universe? Imagine peering beyond the boundaries of the Standard Model, physics' intricate map of the subatomic world. For decades, this model has predicted particle behavior with stunning accuracy, but frustratingly, it leaves us with puzzles unsolved. Why is there so much more matter than antimatter? Where does the elusive dark matter hide? Are there forces at play that remain invisible to our current tools? Here's where things get thrilling, and yes, a little controversial. One way scientists hunt for new physics is by scrutinizing particles with a level of precision that borders on obsessive. The idea is simple. Measure every property as meticulously as possible, then spot any mismatches between theory and reality. Every tiny discrepancy could be a hidden clue, slowly piecing together a grander world. More complete picture of the cosmos. Let's zoom in on a lesser-known family of particles, charm baryons. Specifically, the lambda C+, lambda C+, a hefty relative of the humble proton. These are complex conglomerates made of 3 quarks, up, down, and the heavier charm quark. Simultaneously fascinating and elusive, they survive for less than a trillionth of a second, 10 to the minus 13th. That mind-bogglingly short lifespan turns experiments into high-speed races, with physicists scrambling to record data before the particles vanish. Because their properties are so tricky to capture, there's still uncharted territory and perhaps new physics lurking in the gaps. What's especially compelling about these particles are their electric and magnetic dipole moments. While earlier particle studies have repeatedly tested our best theories and occasionally shocked physicists with unexpected findings, charm baryons remain a largely untapped proving ground. Could their dipole moments reveal cracks in the Standard Model? Here's the part most people miss. Conventional methods using powerful magnetic fields just aren't up to the task. These fleeting particles pass through so quickly that standard equipment can't measure their dipole moments with much accuracy. This challenge demands a radical new approach. Enter the groundbreaking idea of double crystal channeling. The key lies in the tidy, orderly arrangement of atoms within a crystal. Seen from just the right angle, these atoms form narrow, straight channels through which charged particles might travel. When you bend the crystal, these channels curve as well, steering particles along a new path, something previously impossible in such a short distance. If you can guide these short-lived charm baryons using not just 1, but 2 bent crystals in sequence, it opens the door to measuring their properties with a precision never before achieved. But this concept isn't just theory anymore. The TWOCRYST experiment was devised as a proof of principle, essentially a bold test to see whether this scheme could work outside of simulations or blackboards. After just 2 years of preparation, researchers installed TWOCRYST in the Large Hadron Collider, LHC, the world's highest energy particle accelerator. The setup is surprisingly streamlined. 2 carefully aligned bent silicon crystals, a tungsten target, and a pair of ultra-precise detectors, a pixel tracker and a fiber tracker. Here's where the friction begins. The very notion of double channeling, deflecting particles through both crystals, was unproven. Would the delicate alignment work in the chaos of a live accelerator? In June, the team fired up the experiment at an energy of 450 gigavitts. The result? Success. All equipment operated flawlessly and for the first time at the LHC and at unprecedented energies. They observed particles that had been double-channeled. Is this the edge of a new experimental frontier? More tests are on the horizon at even higher energies. The next steps are crucial. Researchers will analyze whether enough bent, charm-carrying particles are produced to justify an expanded experiment. Even if this run doesn't lead straight to a physics revolution, TWOCRYST has already set the stage for more innovative uses of crystals at the LHC and perhaps at future accelerators. But let's throw out a question to all you science enthusiasts. Could this two-crystal method uncover quirks in particle behavior that force us to rewrite the textbooks, or will the Standard Model emerge unscathed yet again? And here's something for debate. Are radical new experiments like this worth the risk and investment, even when results are uncertain? Share your thoughts below. Should physics bet big on bold ideas or stick to safer, well-trodden paths?